for constructing a rectangular portal. One side of the portal will be formed by a barn and requires no fence. 3 exterior fences and 2 interior fences partition the portal into 3 rectangular regions as shown in figure 4.51. What dimensions of the portal maximize the enclosed area? What is the area of that portal?
Okay. So, this section 4.4 optimization, it means to find the dimension. Well, in this case, it will be the dimensions that will maximize the space based on perimeter and area. So when you hear that optimization, it's going to involve like a math sort of thing, correct? And so how do we find those quickly? By creating an equation and then finding the derivative and then setting the derivative to 0, the first derivative, and then solving for x, right? And then we have to determine if it's a max or a min, but whatever. So with this problem, as I said, we're going to use both perimeter and area. Why perimeter? Well, because we know how long of a fence it has, right? And then I know you have the drawing there, but just try to imagine you don't have it, okay? And so what he wants to do is to have 3 exterior ones. So that will be like 1 here, 1 there, and 1 there. And then it says something about the barn, right? Do you guys understand that part? Mm-hmm. That it's against the barn, so he doesn't need that wall right here. So then he wants to divide it 2 interior fences, right? And 2. So something like that. So now, because of that, we know that all of these ones will be the same. We'll call them x, 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 and then this one will give it another name, y. And what do we know about the perimeter? In this case, I don't want you to just think about the outside, but also the inside, like if you were to trace every single wall. Yes? So then how many x's do we have? So the perimeter will be 4x, right? And then we also have 1y. And so, of course, that's the equation you have here. That's where it's coming from. Now, we also know that he has 400 feet of fence. So that will be 400. Okay, so now what we're going to do is we're going to solve for y. Because we just want to have, we want to derive with respect to one variable instead of doing implicit and having the rest. Or, I mean, if we do that, it's the same thing. So we could have y is equal to 400 minus 4x. Okay. Now, how would you guys get the area of a rectangle? That's very easy, right?
It's length times width.
Length times width, so x times y. So for the area, xy. Now, what we're going to do is substitute the y with the expression that we have here. The one that came from the perimeter. Yes. So that way we have x still here, but then instead of y, we replace that with the 400 minus 4x. Yeah, is that clear? That is taking place of the y. Okay, so then we can distribute the x, then we'll have 400x minus 4x squared. And so that's going to be the area. Now, if we find the derivative of that one, you guys know how to find it quickly, right?
Negative x squared minus 4. No, negative 8.
So let's say I'm going to call it, since we're calling this A for area, I'm going to call that dA over, what are we deriving with respect to?
D1. No, dx.
dx. So we're taking this part and this part. right? And deriving. So what's the derivative of 400x?
So it's gonna be negative 8x.
No.
Well, I'm getting it backwards.
Okay,
Okay,
400
minus 8x.
minus 8x. Okay.
It doesn't bother you though? No, the x isn't, no, it bothers me.
Well, I kind of like it because the negative is not in the front. But I mean, I understand. Okay. And then, of course, we have the equation of the derivative. I'm sorry, of the area right here. Right? And then now we found the derivative just so that we can find that point, right? And we know it's going to be 50, but pretend you don't know that yet.
Okay.
So what do you do? What's the next step?
Equals the formula 0.
All right. So we want to see when that slope will be 0, right? Because we're looking for this point, the turning point. And so it's pretty simple. 400 minus 8x. I could take the negative 8x to the left. Then it will be positive. And then x will be 400 over 8. And that is how we get 50. So if the rancher uses like the two exterior walls and the two interior ones that are the same, the ones that we label as x, if he uses the dimensions of 50 feet, then what will be the area?
So you just plug in that number?
Right here. Right here in the area formula. So if you find the area at 50, it will be 400 times 50 minus 4 times 50 and then square. And just to save us time so we can cover more problems, the answer is right there. So that will be the maximum area. So that is actually like, when you talk about the max and the min, you have to give the output value. That's the maximum area. And so that would be 10,000 square feet. Now, what if the question was, what will the wall parallel to the barn will be? Like y. What is y?
Well,
If you know x, what did we say x should be?
X is 50, so y equals 4 times 50. Or
100?
Well, don't we have an expression for that?
No, we do, I'm sorry.
There you
So
go.
just plug it in. Oh.
Correct. So do I? What do you get?
200.
Yeah.
Yes.
You'll do it? Okay, so no. So that is what? 200. And we had 400 feet of fence, so then y should be 2. I believe it. Okay. And that's it. So that's how you can apply it to real life when you buy your own ranch. Believe it or not, that's our common problems.
Thinking, find a ranch?
No, like for people with cattle or.
Because you have to take care of the line.
All right, now number 2. Who would like to read the next problem? Oh yes, I'm so sorry.
Forget it till you wait now.
Kayla.
Oh, suppose an airline policy states that all baggage must be box shaped with a sum of length, width, and height not exceeding 64 inches. What are the dimensions and volume of a square-faced box with the greatest volume under these conditions?
All right. So pretend you don't have the picture, right? Don't look at it. Don't look at it.
Searching it out.
And so it's a square base, right? And then it goes up. Oops. This might not look good. I don't know.
Why don't you just trace it and say you
Okay. There we go. Let's trace it. So here's the square base, and then with a sum of length, width, and height not exceeding 64. So if we were to add the length plus the width plus the height, it will not exceed, so less than Could it be
Equals?
64? Could it equal 64?
Yes, it just can't be bigger than 64. Okay.
What are the dimensions and volume of a square-based box with the greatest volume under this condition? Okay, so if they say that it is a square box, then, I mean, it's not a cube, but if the base is a square, then you will know that two of those are equal, right? Two of the dimensions right here. So this L, we're going to change it to a W. Okay. So then, we have that, if we combine like terms, you get the 2W plus H. And let's just put an equals. All right. So then from there, to calculate the volume of a prism, base times width times height, or length times width times height, right? So it will be for the volume, length times width times height. But we already established that the length and the width are the same, right?
Would it be W squared times height? Right?
Correct. So this 2,
Oh, it's right there. Wow.
W squared times height. Yes. We do have it there. But you guys still need to learn how to get it.
No, I wasn't even looking at this. Okay, then.
All right, so are you guys comfortable with how we got the formula?
Yes. Okay, so now we just need to find the maximum volume.
Well, let's reread the question. So, actually, we haven't even read it. What are the dimensions and volume? Well, yeah, here, let's do it. What are the dimensions and volume of a square base box with the greatest volume? So, yes, we do have to find the maximum volume. And we have to find what dimension will give us that, right? So then, what we're going to do first is we just want to use one variable, okay? And so what we're going to do is similar to what we did on example 1. We're going to take this equation, and this one is easier because it's just linear, and we're going to solve for h. And that would be h is equal to 64 minus 2w. Then we're going to go back here and we're going to substitute that h with that expression. So that becomes the volume is the width squared times 64 minus 2w. That is taking place of the height. So now we're going to distribute the w squared, and that will become 64 w squared minus 2w to the third power. Now from there, we're going to take the derivative. So in this case, we're going to call it dv. So we want to know how fast is the volume changing with respect of the width. Correct. And we can do that because we turn the length into w, and then we turn the height into an expression with w. Yeah? Does it make sense? So we have to do that because we just want to have one variable here, w. All right, so then derivative, very simple, 128
W minus 6W squared.
Oh, I was thinking 2 cubed. Minus 6w squared. Thank you. Okay, now you guys find the max in this case. I know you have the answer in the phone.
I'll check that.
So remember, you equal the derivative to 0. What can we do here?
We just created a
Oh, factor. Can 128 be divided by 6? I don't know. Can we check quickly? Because if we can, we can just take the 6.
No, it's only 64.
That's 64.
Which is 21.3.
Okay, so we just factor w out? Okay. So 128 minus 6W. So of course from there, you already know that you can get two solutions, right? One from each chapter. But we're talking about a box, and we don't want that to have the width of 0. Right? So we don't really take that solution.
Wait, we just solved the other.
Right? Because it doesn't make sense. No box will have that width. Right? And then for the other one, we take the factor equal to 0, and then we solve for W. So 128 is equal to 6W. So W is equal to 128 over 6.
Oh, I already said the answer.
And that is the 64 thirds. What is like a decimal approximation?
Oh, 21.3.
No, that was a 1.8. Oh, something. 21.33. Okay.
0.1
What happens if like you're on the exam, they don't care about you rounding or using the little line on top. They just want you to use 3 decimals, and they call this process truncating. Not truncating. Truncating.
Can I put 1/3?
Like this.
Can I put 1/3 or no?
Oh, yeah, makes sense. As long as they are equivalent. I mean, in fact, if it's an open-ended question, you can do it like that. It's perfectly fine.
We're not done yet,
Well, that will be the dimension of the width.
Okay.
And in fact, it would be better if you use the exact solution, which is the fraction, to find the maximum, what are we talking about? Volume in this case. And so we use a function for volume, the one that we found here.
W squared times V? Oh, yeah.
The 64 W squared minus, what is it, 2 W cubed? Yes. It's also here. Remember, we found it from here. After we substituted the height with the expression for W.
Yeah.
There we go. And what are we finding? Sorry for that. Okay, so you substitute your 64 thirds there. If you have the opportunity to use a calculator, please use it.
I'll do it later.
If you do it in your head, make sure you square both numerator and denominator, or in this case, raise to the 3rd power the numerator and the denominator. Okay, don't forget that, please. Practice typing it all in your calculator. Don't be lazy. All of you. All of you.
Eric, what's calculator?
Oh, do you have one?
No, I'm just kidding. I wasn't even looking at it.
Well, yes, because like you guys are just waiting for Kayla and Aya to give us the answers.
Yeah, guys. What does it look like? Geniuses?
Yeah, you did.
Alyssa, we miss you.
Oh, I'm looking
We
at
hope
it.
you get better, Alyssa. And Alvin. We don't know why Alvin got sick.
Wink.
Wink.
Alyssa.
Oh. We don't know why Alyssa got sick.
Yep. Okay, cool.
Okay, so what is the maximum volume?
The numbers, or do you want the fraction?
Give me both.
The fraction was 262,144 over 27.
And the approximation?
9,709.037 repeating.
Okay, we can just stop there.
I mean, there's more.
And so that way you don't have to worry about like, do I round it to an 8 or leave it like, you just drop it, like right there. Like you just.
You go off by 1 point. Did you pick up points?
No. That's why they have that rule. You just shrunk, probably not with a K. Shrunk.
I think it has a P.
Okay.
Why should I even listen to this video?
What are the units?
Inches cubed.
That's very important when you give your final answer, guys. Okay? They do take points off for all units. Okay, so let's move on to the next one. Oh, you guys need to.
What would happen to you anyways, on Wednesday?
Okay. So who wants to read the next one?
Eric.
Oh, never mind. Those are the guidelines for optimization problems. So we'll read them for this. Okay, so Eric, number 1.
Read the problem carefully, identify the variables, and organize the given information with a picture.
You take the next person.
Identify the object
Objective.
function. The function to be optimized. Write it in terms of variables and
That's when we like substitute one variable for the other expression. Like when we substitute the height for the depth.
Oh.
Okay, number 3, you want?
Identify the constraints. There's some variables of
Well, what do you guys understand by that? Identify the constraints.
Like kind of equation, no?
like how we did with the songs where they were telling us you have a limited amount of like the base and the length and width and the height cannot be more than 4 inches, or he only has 400 feet to work with.
So the first problem we did was only 400 feet of gas. Right? So okay, number 4.
use of constraints to eliminate all but one independent variable of which.
Oh, that's when we do the substitution. Sorry, guys. Okay, number 5. So, for example, going back to number 2, that would be when we write the perimeter and the area, like volume. Okay. Number 5. What do you want, Martin?
The different function expressed in terms of a simple variable. Find the interval of interest for that variable.
So, what do we understand by that? Find the integral of interest to that variable.
So like with the problem with the baggage, we wanted an interval of like from 0 to positive numbers, but not including 0. The 0 to 0.
Yes, because we're talking about dimensions, so very good. So sometimes some of the, even though like your function might have a domain of all real numbers, you don't want to do that, right? Because it has to fit the problem, the context of your problem and your variables. Number 6. Who has it right? Tiffany.
Aww.
These methods help us find the absolute maximum or minimum value of the objective function on the interval and
Of
interest. If necessary, check for endpoints.
It could be like interval of interest, like restricting your domain, for example. Okay. And then it was the same. Check the endpoints. Very good. Okay. So let's go to another problem. Who would like to read it? Okay, thank you.
Suppose you are standing on the shore, circular pond with radius 1 mile, and you want to get to a point of the shore directly opposite of your position on the other end of the net. You plan to turn at 2 miles per hour from your current position to another point B on the shore, and then walk at 3 miles per hour along the shore to the terminal. How should your speed minimize it?
Okay, so don't worry if you read a problem and then you don't really understand what we're talking about. That's very common. In my case, maybe I got a little distracted. I might have to read it again. Right? Or so you have to like sometimes break it into chunks or go sentence by sentence. And it's always good to reread the question. I know that sometimes in elementary, teachers tend to tell you to read all the questions first and then read the passage. Zansuela hates that here, by the way. But with these problems, I'm not going to say read the question first. But after you read the problem completely, you might want to read the question a second time before you reread the problem again. It kind of helps. So you know what they want you to find. So they want you, how should you choose? Here's a question, it's usually at the end. How should you choose P? What is that going to be? Okay, we'll figure it out. Oh, right here. To minimize the total time. Now, even though the total time of the trip. So even though it says minimize, we still gotta do the same steps, right? Because it's just optimization. You find the equation, derivative, equivalent to 0. So let's see what they're talking about. So you're standing here. If you're a guy, I'm sorry. And so the circular pond, you guys understand that, right? So like a tiny lake with a radius of 1 mile. And so the radius, you can see it here. And since it is a circle, it is one radius in any direction. You want to get to a point that is directly opposite. And so from here, we know that from here to here, and here to here, will those be the same distance? Yes. Well, if we go across the center, they should, right? So let's see. You plan to swim at 2 miles per hour. Oh, and actually, we know exactly that, yes, they are going across the center because it says on the other end of the diameter. So yes, that's for sure.
So, make it to the other side.
So how many miles is that?
2.
If she just went straight 2 miles, right? 1 and 1.
Only
Okay.
3 hours.
So from your current position to another point, and then walk. Oh, so she wants to, instead of swim the whole distance, because it will be 2 miles, she wants to take a shortcut, because perhaps this person can run faster. So then she's going to go from here to here, and we don't really know where this point is, okay? This is actually the whole question. How to choose that point to minimize the total time for the trip. So far we know that her swimming speed is gonna be 2 miles per hour. Now let's see what else the problem contains. And so after that, she's going to walk after arriving to that point, she's going to walk from that point to the finish line. And what is her walking speed?
3 miles.
So see if she can walk faster than what she can swim. I don't know if that makes a lot of sense, but I don't know.
Maybe she's
Do you guys know your swimming time?
Yeah, I get it.
What's your swimming time?
Oh, no, not swimming, I understand why she.
Oh, okay.
Maybe she can't swim for an hour.
No, the idea is that she doesn't want to get out of the pool earlier because going around the circle is actually going to take longer. Because it's more of a distance.
So let's imagine,
What?
you guys, if we know the radius of the circle, could we know the circumference? It will be what? Pi times diameter, right? So we already know the diameter is 2 miles, so it will be like pi times 2, so like 6.28, let's say. So that is what she will do, but considering that she will only go like half a circle,
That'll be pi.
that would just be, it would just be pi, right? Or approximately 3.14 miles. If she was to go just walking, correct? But if she just swims across, it's gonna be 2 miles. So she's trying, this is only walking. Only swimming 2 miles, so she's trying to cut distance and time by her different rates of like her speed swimming and her speed walking. So then she's trying to position this point so that it's like the minimum time possible. All right. So let's see.
Oh, she's lazy.
I'm gonna just read this from the book, okay? The objective function is the total travel time as it varies with theta. What is angle right here? Theta. Right? Why? Yes. Why? Because if you position your point right here, then that angle is bigger, right? But what do we know is that this straight line, what is the angle measure? 180 degrees, or in radians, high. And so that is why it doesn't matter what the angle is so far. We're just going to call it this one, theta. All right? And so since together they form 180, that's why we have, or pi, that's why we have pi minus theta. Yes, that makes sense? Okay. So now let's see what else we can get from here. So we're going to use the, you know that for, let's say for speed, if you look at your speedometer in the car, it's always the distance over the time, correct? Now we're going to call them rate. Instead of speed, I'm going to call it R for rate. So it's d over t. So how can I solve for t? Because that's what I'm trying to minimize, right? So remember how with the other problems we were trying to maximize the area? And with the other one we're trying to maximize the volume. Now we're trying to minimize the time, so that's why I'm going to solve for t here. Okay? And so if I do that, it will be RT is equal to D. Or solving for t, it will be t is equal to D over R. Okay. Now, we're going to include geometry. Are you guys ready?
Yes. Okay.
It's actually almost time.
So continue.
We have time?
Let me just read this.
Okay.
The length, okay, wait. For each leg of the trip, one leg of the trip means like the swimming part, okay? The other leg of the trip means the walking part, okay? Yeah, you guys follow me? Okay. Now, for each leg of the trip, the travel time is the distance traveled divided by the speed. Okay. We have it here. The rate, speed and rate. Yes, are we okay with that? We already got that. So then, we need a few facts from circular geometry. The length of the swimming leg, arc length, yes, thank you. So for length of the swimming leg, we're going to use is the length of the chord of the circle corresponding to the angle theta.
Can you say that again?
Yes. The length of the swimming leg is the length of the chord of the circle corresponding to angle theta. Okay? And so that one,
So the chord length of the arc length are equal?
this is a chord.
No.
This is a chord.
Chord is
Yes.
two lines that is a 2 points.
Oh,
and
okay, so it's
equal
just saying
distance.
it's that long.
Right there.
Yes, okay.
That is the chord.
That makes
Okay? And then the length of the swimming is going to be
The
a
arc length.
arc length.
Oh.
So we'll
okay.
solve this one next class because I don't want to ruin your Wednesday. Yes. All right. So
I actually love